if that's okay with you, Greg and Andy.
Absolutely.
Yeah.
Yeah. And you'll notice I've got my little fancy background up here. Please feel free to copy down that email. We're going to be sending you out some of the things that Andy discusses today too via email. But please feel free to contact me in particular, because if you send it to Andy, he'll just send it to me. So just go ahead and skip the step and send it to me if you would. Any kind of requests or questions that may come up later too.
Okay.
But great question, Melanie. Thank you.
All right. Well, I will get started. All righty.
Thank you.
Yep. I don't have a fancy background like Greg. I'm working from my basement, as you can see back here. But thank you so much for inviting me. Yeah, I'll be giving you sort of an overview training in Mathematica today for about an hour, maybe 15 minutes or so. I am one of the trainers in the department, but Greg is your main point of contact for licensing, for access, distribution, that sort of thing. He mentions I'm a education expert. I don't know, but he is the licensing expert for you. So any questions you have about any of our technology products, he is your guy. So feel free to refer all of that to him. He's got the information about what your university has and how that all runs. So he'll be that guy. But I'm happy to answer questions as we go along about Mathematica itself. As Greg mentioned, I've been here for more than a decade. I'm in my 13th year working with campuses like Roosevelt that already have access to Mathematica. So it's not my job to convince a campus for the first time that we're a great and useful technology. I'm here to support current users, help find new users to take advantage of the license you already have, and to help you explore new features of whatever version we have, or even new pieces of our technology stack. Before that, I spent 8 years as a high school and junior high math teacher in a couple of public schools in Indiana where I never got to use Mathematica. I had a graphing calculator and my students had a graphing calculator set that became incredibly frustrating to use. And so we just didn't use them. But seeing now what Mathematica could do for my students, it would have saved me time, would have been able to allow my students to dive deeper into the material and of course set them up for college when they're going to be using computer programs anyway. So I want to take just about a minute and a half and talk about our company as a whole, because if I'm going to tout the greatness of Mathematica, I think you need to believe it from the standpoint of what kind of healthy company we are. We're used in the world's top 200 universities. We're all up and down the Eastern Seaboard and through the Midwest across the country. The Fortune 50 companies rely on Mathematica. Many of the Fortune 500 companies do as well, not just for computing, but also for presentation, document creation, data requisition, things like that. People know about Wolfram Alpha now more almost than they know about Mathematica. We have almost 2 million people coming to Wolfram Alpha and using it every day. The company was formed in '87. Mathematica version 1 was released in 1988. So Mathematica turned 32 this summer. And we're not just in education, though we were the first product of our type to run on Apple on a Macintosh, which is pretty significant. You know, Nobel Prize winners, 10 of them in physics are using Mathematica. Wolfram Alpha, you guys know it. I'm sure you love it and rely on it. It's built with Mathematica as the engine. And what we're finding out from talking to professors, talking to students, is that though people relied on Mathematica for STEM fields and quantitative areas and anthropology, political science, economics in the past, Wolfram Alpha has allowed computation to move curriculum-wide across the college. You know, there's a professor at Ohio State University that used Wolfram Alpha Pro to compare poems from different authors to look at similarities in sentence structure, verb usage, things like that, which is so far outside of what we consider to be normal computational use, yet it's very easy to do within our software. About 6 years ago, we released Mathematica Online, which is our browser-based version of Mathematica, which is our way to compute with Mathematica on a cell phone, tablet, or from any place where you can get to the internet. Mathematica Online allows you to share notebooks through the cloud. Mathematica Online can actually be integrated within your single sign-on environment in your university as well. As we go through, just for the sake of simplicity, I want to do some definitions. So the the type of programming language we have, we named it the Wolfram language. Because Stephen Wolfram developed Mathematica, he can name as much stuff after himself as he wants to. You know, I think if I developed Mathematica, this would be the Dorset language. You know, I think we would all do that. So, but basically the Wolfram language is our actual language, but also the data that you can pull into it from Wolfram Alpha. And I'm going to use the words Wolfram language, Mathematica code, Mathematica syntax interchangeably. They all mean the same thing. Okay. If you use an iPhone, which I don't, but if you have an iPhone and you ask Siri a computational question, Siri uses Wolfram Alpha to find that answer for you. But building on the popularity and students' familiarity with Wolfram Alpha, we can carry that right into Mathematica. You don't need to know a single bit of programming language of our software to begin. If you hit the equal sign, then you can compute in Mathematica like you're at Wolfram Alpha. So we can say, graph the sign of X. I evaluate this. My Mathematica license is talking to our servers over in Champaign, Illinois, to figure out what those words mean, to give me the result, but also to give me the actual Wolfram language it takes to make it. We can be more creative. Plot sine of X from X equals 0 to 2 pi. With a frame. Let's see if that works. There we go. Great. Now what I can do is I can click on the Wolfram language. When I do that, the equal sign is gone, which means I'm not relying on the connection to Wolfram Alpha to do this any longer. Now I'm actually in Mathematica. And now that I'm in Mathematica, I'm going to try stuff. Sine of 2x. Let's turn that frame off. Let's say frame false. Okay. Maybe I want to say, you know, negative 10 to 2 pi. So this is where students' curiosity can take over, and where now we've got code that we can look at from the beginning, and I don't have to create things from scratch. It makes getting started with Mathematica, getting up and running, very, very easy to do. I'm going to show you some of these rules as we go along, but let's take something like population growth of Romania during the 1980s. Okay, that's fine. I can look at this. We could pull this open and see a little more information. But what if I wanted to view this on a graph? We can take this data that we just asked Wolfram Alpha about. There's this function called date list plot that takes a list of dates and puts them on a plot. We use this last output. And there we can take the data, then we can begin doing computation with it without having to pull in a lot of research, without a lot of extra programming. Mathematica just does a lot of this stuff in the background for us. Another way to get started with Mathematica without having to rely on Wolfram Alpha still sort of uses a feeling of Wolfram Alpha in that it's got this sort of intuitive, I think I know what you mean, Greg, kind of feeling to it, where it makes some assumptions and helps us along. Let's say that I need to plot and find the derivative of this binomial for calculus class, and I don't know the Mathematica commands to do it. I can just type this mathematics and I can hold shift and hit enter to actually get Mathematica to do something. Well, it didn't really do anything. It just returned for me that binomial, but it gave me some suggestions for next things I could do. So remember, I don't know Mathematica. I don't know the rules. So I'm just going to click on buttons and play along. So let's, okay, expand that binomial. That's fine. Maybe let's find the derivative. Okay. Let's put this on a plot now. Very good. Now notice all I'm doing is I'm clicking on buttons. I'm not doing a single bit of programming. I'm just clicking on buttons. Let's add some labels to this plot now. Adding labels is something I don't know that I would be able to program on day one. So let's say Roosevelt University. Let's call this the x-axis. Let's call y. Let's just call it y. Hey, let's choose a font. It'll be fun. Make this size 24 so we can see it. Great. Bold and italic, absolutely. So now let's say I'm done. Click done. And now let's say I'm done with my plot. Well, we can click this little snail looking button to roll up all the inputs. And what it does is it takes all these steps where I click the buttons and it gave me this answer, then this answer, then this answer, put it all together in one plot for me. Now that I see this, I realize that it looks pretty ridiculous. So I want to change some of it. So that font is way too big. That's better. Italic is fine, but bold is too much. I'm just going to delete bold. Great. Where did my mouse go? There it is. And now maybe let's make the x-axis look like the y. Fine. Oh, I lost my mouse again. And what if I wanted to actually change the function? Okay, well, let's choose that as well. Why am I doing all this? The idea is that this next suggestions bar and this predictive interface allows my students to be curious and learn and do things with Mathematica. Then we have the Wolfram language there where we can change it without creating it from scratch, where my students are learning the workflow of Mathematica. They're learning the concepts that I'm trying to teach them without having to do everything from square one, which saves a lot of time. And it gets students engaged in the technology so that Mathematica isn't just another thing they have to learn. It's actually a useful part of what they're doing day to day. But you're going to want to get them to actually build things in Mathematica. So let's look at, there are 3 basic rules. Functions are always capitalized in Mathematica, whether it's a Mathematica function or something mathematical or in science. Oops, excuse me here. Square brackets always go around the thing that you evaluate. So I'm finding the cosine of x, so that goes in square brackets. Curly braces always go around any lists or ranges that you have. So where x is defined, this is surrounded by curly braces. So let's put this in action. How does this work? Okay, students, I want you to plot, cosine of x from scratch. Okay, let's use our 3 rules. Functions are capitalized. Let's start with a plot. As I begin typing, just like Google does, we try to help you out with next suggestions. So let's click the first one. And in this menu, let's just choose the first option. And Mathematica makes a template for me. This is one of my favorite features in that I don't always have to know the grouping symbols or the pattern. I think of this as Mathematica and training wheels, if you will. There's another way to create a template. Way up at the top, we can click on palettes, basic math assistant. Let's do something in 3 dimensions now. So we'll click on plot 3D. And again, we get a template to build a 3-dimensional plot. Before I build this, let's look at the pattern. Mathematica is all about patterns. So we have the name of the plot, the thing that I'm going to plot, and then the definition of the variables. They all follow the same pattern. Once you know how to do one type of plot, you really know how to do all plots. So let's go ahead and let me throw something up here. X, Y, as X goes from 0 to 4, Y goes from 0 to 4. I'm just tabbing between buttons, between boxes. When I evaluate this, I get a really attractive 3-dimensional graph. I can grab it and rotate it. I'm trying to rotate it. There we go. And with just a little bit of Mathematica knowledge and just a half a line of code, I've created this really attractive 3-dimensional graph. Now, before I move on, I wanted to say a couple of things. First of all, Zoom eats up the virtual memory and the bandwidth of your machine at all times. If you were running this without going through a Zoom presentation, you'd be able to grab that 3-dimensional plot and spin it around and see it very quickly. So any sort of lag here is because I'm using Zoom. Number 2, I'm presenting in my basement, and I'm just about as far away from the Wi-Fi source in my house as possible. So there's a little bit of slowness there as well. The other thing I want to mention is you'll notice if you're paying attention, I put a space in between X and Y. If I don't, you'll notice it changes color and excuse me, blue is Mathematica's identifier for undefined. All right, in algebra, xy means x times y. In Mathematica, xy means xy. It's one thing. So a space means multiply, or of course the little asterisk, that means multiply as well. Questions so far? All right. In my days of teaching pre-calculus, after I had long abandoned the graphing calculator, my students reluctantly graphed everything I wanted them to graph by hand. I wanted them to see things like, when the number in front of the x gets bigger, the wave compresses in. This is algebraic behavior we already know about. But I really would like to show this in motion. I would like to show an interactive model that sort of displays how this runs in real time. We have a function called manipulate, which is our model building tool. So I'm going to grab this plot. Let's just copy it and paste it right in here. Now, instead of a 1 or a 2 or a 3 or 4, I want to create a variable that represents those numbers. We'll call it frequency, FREQ. No space because FREQ is one thing. I really like that. It makes the variable descriptive. So let's call frequency a range of values from 1 to 5. Oops. Very quickly before I evaluate, this is what my sign plot was basically. Manipulates on the left. The definition of what I'm manipulating is on the right. You'll find as I go through that what I do is I build from the inside out instead of left to right. This is how most people run with Mathematica. As I evaluate this, I get a slider. Let me make this larger. As I move this slider, I see this wave compressing, stretching. What I love about this, if I think about this from a teacher's perspective, I'm not circumventing any educational material here. We're not letting Mathematica cheat. They already know how to graph by this point. They know how to put things on a plot. What we're doing is we're getting to the heart of the matter much quicker so I can dive into deeper level critical thinking examples. Let's add another variable. How about plus b? So another variable, I want to add another range of values. So you just comma, another list. B goes from 1 to 10. So this time, here's my frequency. Here I have horizontal shifting. Great. These little plus signs open up animation controls where I can see the value. I can use this to play or speed this up or slow it down. So I've created an interactive model about sine of x. I want to do the same thing for cosine and tangent without making two new models. So I want to modify this model. Let's take out sine and create a placeholder variable. Let's call it trig. Doesn't matter. And let's let trig be. Now, it's not a range of values. It's going to be a list of trig functions. So inside this list, I have a list. So I need another set of curly braces, sine, cosine, and tangent. There we go. You notice some purple. That means I have brackets that are open and not closed. So I need to close those up. So when I evaluate this, oops, what did I do? Just a moment here. Oh, here we go. Sorry, everybody. I I deleted a bracket earlier. There we go. Got it. Okay. Sorry. It is a Friday afternoon. I'm behaving like it, I think. So, all right. So when I have this list of trig functions that I get radio buttons because I've got distinct items in a list. Now I don't need to stop there. Let's add the other three, secant, cosecant, and cotangent. 3 more items should mean 3 more buttons, but actually, once I get past 5 items, Mathematica creates a dropdown for me. Makes my model look very nice and clean. What I love about this is all of the appearance of the model controls are built in behind the manipulate function. All I have to do is follow the rules, and Mathematica does this for me. So in just a few minutes, less than 2 lines of code, I've got a basic trig graph interactive model that shows 2 different parameters. And I haven't subtracted any bit of the learning from what my students know or work with. Let's look at a statistics example. All right. Let's run because I'm teaching a concept, let's have my students run an experiment that will end up fitting into a normal distribution. Okay, so we've got a normal distribution with 100 random real numbers, mean of 0, standard deviation of 2. Okay, I'm using random real numbers, so anytime I re-evaluate this, I get a new set, a new histogram, but it all sort of looks like this bell curve. But the idea I want my students to see is as the population of my experiment gets bigger, if there's a correlation, it's going to be easier to see. Let's make this interactive now as well. So again, I have this manipulate function. Let's say we're going to update the trials. So I'm going to run trials, and it's going to start at 100, end at 7,500. I'm going to count by 5s because I don't want a decimal, part of a trial. I'm going to run a trial. So just like before, I have this slider, and I move the slider, and I see this creating a really nice looking bell curve. The more trials I have, the more it will look this way. Now, Mathematica tries to maximize the thing that you're trying to see in its window. And to do that, of course, it has to update the X and the Y axes, which is fine. The problem is this can be a little bit distracting, and I want to hold the axes steady. So I'm going to teach you your 4th rule now. This is, options for a function. So I want to hold the X-axis and the Y-axis steady. And this is done under the option called plot range. So where am I going to put it? Now that I've got this command, the tricky part is knowing where to put the thing you want, to add. So I think, okay, I want to update the plot range of the histogram. So it's got to go inside the histogram somewhere. When I click right inside there, I see where it begins and where it ends. So right here before it ends, we're going to say plot range. Any function that has 2 words or 3 words, you smash them together and let each word have its own capital letter. Create an arrow with a hyphen and a greater than. Now, plot range. Range means curly braces. So I need a range for the X's and I need a range for the Y's. For the X's, we're just going to let it be -7 to 7. For the Y's, let's say 0 to 850. So now when I evaluate it, I see this builds up, and the behavior all along the way is what I would expect, where the largest is here at the mean at 0. And again, we've demonstrated the statistics principle, less than 2 lines of code, and my students are learning quite a bit about the behavior of an experiment.
Andy,
Yes.
but you are the random real is a random number generator, right?
Mm-hmm.
That is,
Yes.
of course, normal distributed. But is there a way to, for instance, get a skew distribution and see that the when n increase you have
Mm-hmm.
Same to the normal? I mean, to the.
Yeah,
to
let's
the-
see here. It's been forever since I've taken a statistics class. So let's, so if I hover over a function, this
Mhm.
little blue box, the one on the left is the one that built a template for me, but the one on the right takes me to the documentation center page. Okay. So this is the page for normal distribution. All of these examples I can, run through and change if I want to. Let me go down to the bottom and see, okay, we've got all these different types of distributions. So let's say, what about a skew normal distribution? Does the coding look different for a skew normal distribution? Let's see, it looks like it does a little bit. So if I take this and I try to skew, yeah, let's see here. Let me take this off just for a moment. Okay, what if I wanted to do, yeah, this is something that the quick answer, Wilfredo, is yes, you can. For me to put this into an example that will work off the top of my head, I'm not sure if I can do that.
Okay. So,
I wonder what will happen if I just throw this in here and say skew normal distribution, if it will let me do it. Well, right now, it looks like Zoom has effectively eaten up the bandwidth and it's making things misbehave. I apologize. Yeah, so here it gave me an error, which is good. I guess in this case, skew normal is called with 2 arguments, but 3 arguments are expected. Now that I think about it, I guess that makes sense, because if you're going to have a skewed one, you need a third parameter that tells to what, value or to what level it is being skewed. So the fact that it kind of spit this out at me is the right thing. Okay. So let's go on. Oh my, okay. Let's try this, everybody. Let me try to wait and see. Okay. All right. I'm sorry. I may have to restart this Mathematica notebook. Yep, my apologies. All right, let's see. Thanks for your patience, everybody. Let's see if we can skip ahead.
I'm sorry, it was my fault.
No, sir. No. Let's see, where were we? Let's go here. No, there's actually something going on with my computer, because my camera is being a little bit fussy. Mathematica has started to bog down as well. So there may be something that our help desk needs to look at. So no, it's not you at all. So I'm using Mathematica in slideshow mode. We don't want to compete completely with PowerPoint. We can't do that. We don't have all the bells and whistles that PowerPoint has. But what we do that PowerPoint does not do is that we're able to present and change and show a dynamic presentation, and PowerPoint can't do that. I can go through here and I can, documents, and I can actually change while I'm presenting my slide. You're not allowed to do that with PowerPoint. Typesetting is also really, really robust and strong and attractive in Mathematica. A lot of people rely on LaTeX. You may be one of those people that relies on LaTeX as well. That's fine. we can right click, we can choose this cell bracket, we can right click on it and copy the input or the output as LaTeX. You can take the entire Mathematica notebook and save the entire notebook as a LaTeX document. Or many people are using Mathematica as the typesetting tool on its own, where people, create a Mathematica and send it straight to the publisher. So if that's something, if you've ended up arguing with LaTeX or can't quite get Mathematica to make the LaTeX output look exactly like what you want it to look like when you go to that other software, maybe it's time to cut out the middleman. All right. Because of Wolfram Alpha and its connection to Mathematica, you can pull in over 10 trillion pieces of data into your Mathematica notebook environment and run it from here. So I can look at the melting point of caffeine or the structure diagram of caffeine. How many chemicals does Mathematica know about from Wolfram Alpha? Over 44,000, which is pretty significant. What properties can we investigate? Quite a few. So how do we do this? Let's choose a chemical and apply a property to it. So the molecule plot of caffeine. There we go. A lot of people ask us, how often is this data updated? Well, caffeine doesn't really change, does it? No. But about 2 years ago, I was at a campus back when we could travel to campuses, and I was showing this, and for the first time I noticed that it included the double bonds in between some of the atoms here. So when there is an appropriate needed change, when there is demographic information that needs to change or update, or when we just choose to make things more aesthetically pleasing, we change, we build updates here. Let's look at something in the field of demographics or socioeconomic work. Let's look at the literacy fraction of Zimbabwe. All right, about an 89% literacy rate. But now let's go from Zimbabwe to the entire continent of Africa. So we're going to wrap bar chart around this computation, change the country to the continent. And Mathematica builds a bar chart for me that I believe organizes the bars alphabetically. Angola maybe all the way to Zimbabwe. But manipulate is for more than just plots. So we can wrap manipulate around bar chart. We can make the continent a variable so that now we can look at the literacy fractions of North America, Europe, Asia. So going from one idea to something broad very quickly with just a little bit of work with the same set of rules and processes to think through it as before. But you have your own data. You've got data that you collected from labs or from your research. We want to incorporate that into Mathematica and investigate. So how do we do that? Well, here are all the formats that you can natively import into Mathematica. I don't know if you work with any 3D printing to build 3D models and prototypes to investigate. If you do, 3ds and let's see, where is it? STL. These are the most common ones. We interact with those pretty well. So let me show you how this works. So I've got some data sitting on my desktop in a folder. So we're going to go to Insert and File Path and find it. By the way, when Greg sends you an email, he'll send you a link where you can download this entire Mathematica notebook, and you can have this entire file folder of stuff to work with. All this stuff here. Let's choose this spreadsheet. It's a small spreadsheet, but I'm going to take this list of data and put it on a plot. That's what we call it, a list plot. And there we have it. So I could probably do something like this in Excel. It's not this intuitive. The graphics would not be this attractive, and it would not be this easy to do. So we can go from a list plot to a list line plot very quickly. Later on, what I'll do is I'll do a best fit curve and show you what this looks like. If I have time, I'll make time. All right. Mathematica as a symbolic software program. This is what we've been since day one. This is what we've been known for. Here we have an indefinite integral. Here we have the same indefinite integral. And finally, in version 12, we have the constant of integration that we can add on at the end. Solve partial derivative equations. Let's see here, or expressions. Here we've got the a generic polynomial we're going to solve to find the quadratic formula. Here's a physics example. This is a set of differential equations that describe a linear damped pendulum that swings back and forth without any damping factors. So we get the height here and the height here, nothing to slow it down until I add a damping factor in and I see it begin to slow down with each pass. A really dynamic way to show this idea. It's just a little bit of work here. So that's symbolics. Now we use our symbolic strength in the back end of Mathematica to do numerical work very easily. So this function right here does not integrate very well by normal methods. There's no U substitution that will work. So I need numerical methods. So there's a function instead of just integrate, we can use n integrate. These functions that have n in the front are called super functions, and they have algorithms built in the back end of them, which allows Mathematica to analyze the function to choose the correct algorithm for that function to give you the most precise and often the quickest answer. Now, oftentimes, you can have Mathematica tell you what method that it used. Now, if you want to, you can choose your own solver. You can add that on just like I added the plot range. But maybe you want to find out what method it used. So what I did was I took the above graph and I deleted everything that except the actual system of equations. Mathematica tells me that it used, in this case, the Hermite function or the Hermite method to solve the system of equations. So if that's important to you to find the method, that's fine. If not, you can just trust Mathematica to get the right answer for you. I only have 15 minutes left. I want to skip through some things and I want to try some things out. Matrices, it's really easy to build a matrix in Mathematica. We can go to the palettes menu. Let's again choose basic math assistant like I used for building that 3D plot at the beginning. Click the matrix button, add a row and a column, and I can just tab through here and get my values. There I have a matrix. We can do operations on the matrix. So let's say inverse of the previous output. That's great. Or we can find the determinant of that. Easily done. You know, since we're a symbolic software company, we can include some variables here. Let's just make this look really gross. How about some imaginary numbers? Well, let's throw a pi in here too. Why not? So now we can find the inverse of this, which is horrible, but Mathematica does it very, very quickly. Let me show you something else too. We talked about some error messages earlier. Let me show you one that will fail as well. So I've defined matrix 1 as 1 through 9. So now let's see here. What I want to do is find the inverse of matrix 1. This matrix should be singular, so it shouldn't have one. So if I get an answer, that's bad news. Mathematica says, no, this matrix is singular, and it returns for me just literally the inverse of this matrix, which is what you want. You want this to shoot a problem at you because it can't solve it for you. You want this error message, and Mathematica does it for us very easily. All right. I have 15 minutes left, so I'm going to scoot through here. I'm going to quickly talk about 3D printing. Then we're going to go to statistics and some machine learning, because those are probably the most interesting to this group. In version 11, we included the ability to interact with 3D printers. In version 12, we improved. So I'm not going to run through these, but I'll explain what's going on. So let's say we pull up or look at a prototype of something in 3 dimensions. So the typical Stanford bunny, great. But maybe there are weaknesses in the mesh. So we can ask Mathematica to find the defects, and it identifies them for me. We can use the function repair mesh to build different functions in 3 dimensions to sort of fix the problem that it found before I send it to my 3D printer in the next room over, or to an online company that will build the models and send them to me. So the ability to fix the problem with the prototype before I print it out saves resources, saves time, and it helps you get to the end result much more quickly. All right. Let me talk about statistics. Again, I've got about 3 hours of material here, and you'll be able to run through these on your own time and at your leisure. And if you have questions, you can ask Greg, and he can answer. He can consult with me about the things that I didn't show. There's just so much to cover. People don't assume Mathematica is strong in statistics because we aren't usually labeled as a statistical package, like some of our competitors like SAS or Stata or SPSS or S+. Mathematica is just as strong in statistics as it is in calculus commands, image processing commands, programming, that sort of thing. So let's take this data that we pulled in earlier, this basic spreadsheet. Okay, now I want to do a best fit curve, because why else would I collect data unless I had some sort of relationship to fit to it? So this looks like a logistic model, but I don't remember the setup for a logistic model, so I can choose a cubic polynomial to go through these points pretty easily. So we have quite a few different types of fits. Linear model fit is a pretty nice one that works well. So I'm going to define the model and use linear model fit. So the thing I'm going to fit are the values of this data. Here is the framework for a cubic polynomial, and x is my variable. So here is Mathematica's best fit. Great. The function show says put this on top of this. So we're going to take the data that I pulled down from the cloud up here, and I'm going to plot Mathematica's best fit and overlay them on each other. And you'll see Mathematica did a pretty nice job of fitting the data to a curve. So let's see here. Here are all the properties we can look at. We can look at the ANOVA table. Maybe the R squared value. That's a pretty close to 1, so it's a pretty well fit curve. We can look at the confidence intervals. When it comes to probability and expectations, so here let's we talked about different types of distributions. Here we have a Poisson distribution, and we can represent it symbolically. Or let's flip a coin. Because we have heads and we have tails, this would be your classic binomial distribution, right? We would expect a 50-50 shot, but what if I wanted to represent this? Oh, hold on. Yep, 50-50 shot right there. What if I wanted to skew this just a little bit? We talked about a skewed distribution so that I get between 60 and 80 heads instead. Okay, well, I don't understand what that is. So let's find the numerical approximation. 0.03, so about 3%, 3 out of 100. What does that look like? Well, if I look at my graphic, this portion from 60 to 80 represents a very small amount of this distribution. So I could imagine that is about 3% of the total. So it makes sense. Now, when it comes to statistical distribution, I just want to show this very quickly before I move on to machine learning, and that is that Mathematica is a strong statistical software package. So this graphic is from version 11, which is our last major release. Here are all the names of the parametric distributions that are built into Mathematica. And then here are what some of our competitors have. So here we've got MATLAB, not toolboxes, just MATLAB, just R, no extra databases, just SAS, S+, and Stata. You may not ever need to use some of these, like the GUE distribution or the Wishart distribution, doesn't matter. It's here when you need them. Finally, machine learning. Our colleagues across the aisle in the commercial and government sector are using Mathematica for many things, but the big three are for statistical and data analysis, image processing, and machine learning. These are and within machine learning, we have neural networks as well. But machine learning is where things are at these days, and it is very easy to do these sorts of tasks inside of Mathematica. Here's a basic example from the documentation in Mathematica. Basically, a bunch of handwritten numbers that were assigned to what their actual digits are. So what I'm going to do is I'm just going to evaluate this. And so Mathematica is going to now teach itself this data set. So it's learning that, that handwritten 6 is a 6 and that handwritten 9 is a 9. Great. Let me scroll back up just a bit. I mentioned before in integrate, in solve value. Classify doesn't have an n in front of it, but it's one of those super functions that has algorithms built into the background that it will pull out the right one for the situation that you're having it classify. In this case, logistic regression is the one. Now, this 4 I created on my own. I went up to graphics and drawing tools, and I took the mouse tool and I drew a 4. I think it's this guy here, or this guy, I don't remember. It's been a while, but I basically just drew a 4. Now, will Mathematica remember from the data set enough 4s to think that this is a 4? Yes, it will. All right. Let me back up one tick just a minute. Our research applications are plentiful. We have lots of image processing tools and capabilities. For engineering, control systems, control theory was an addition back in version 8. It was a package that you had to buy and add on to Mathematica. It was really expensive, and now it's something that is part of our software program standard. Time series is becoming integrated into Mathematica slowly over the years. Wavelet theory is another one that was a separate add-on package that now is part of our software program used by a lot of neuroscience professors. And yeah. All right. So let me wrap up. Let me end with a few resources so that we can have a discussion about what your goals are, what you would like to do with Mathematica. If you want to look at cloud access to Mathematica, you mentioned the Wolfram Alpha Notebook. We can show some of that. But I wanted to mention just some resources to how do we learn Mathematica. So the best place to go to learn Mathematica is our hands-on start. This video, the presenter teaches and then asks you to pause so you can try out what he did. You can usually work through it in about an hour. This is a great tool for professors to add onto their first week of classes on their syllabus. If students watch this, then they know how to hold shift and hit enter, capital letters on function names, how to create text and title headers and things like that. So you don't have to teach them that as the professor. That's something you just want us to teach them so they know for them to use while they're in your class. Once you get your Mathematica feed underneath you, we have dozens and dozens and dozens of free on-demand tutorial videos at Wolfram U. All right, so for instance, let's look at data visualization quick start. For the majority of these, they're usually between 15 and 45 minutes. In this case, you can download the presentation notebook so you can follow along with the presenter. This one is free. I'm going to make up the statistic. I would say about 80% of the videos at Wolfram U are free. So do not pay for a video until you watch some free ones. I don't want to take money out of your pocket, Greg, but the truth is don't pay for videos yet. Now, if there is one that you see that you want to attend that is a for purchase video, don't do that. Talk to Greg. He can get you a bulk discount if you can get 5, 10, 15 people to attend it as well. You have a site license for Mathematica, so one of the benefits is you have a Greg that will help you find a deal to make it worth your while. Finally, I want to show our books page. This books page, if you're looking for a textbook that includes Mathematica examples inside it, you can start here, and then from here we funnel you off to Amazon.com. Let me show you an example of one that is one of my favorites. A Mathematica Primer for Physicists. This is a book written by a professor that I work with, actually. He actually mentions me inside the book, which is pretty cool. I'm famous. No. This is actually a great textbook for students who are taking introductory physics, and it's in the physics classroom where they're learning Mathematica for the first time instead of Calculus 1. So this is, you're going to start with physics, you're going to start with Mathematica, what's important to you from a physicist's point of view. And it's a great resource. But if you're looking for like just a supplemental book about Mathematica itself, we've got a lot of tutorial books. This one, for instance, is basically How to Learn the Wolfram Language, written by Stephen Wolfram. It's got like 50 some chapters, and it's just a bunch of, a little bit of lecture, a little bit of demonstration, and then exercises. In fact, I've got a copy of it right here. This is an older version of it, but like one Christmas break, I was caught up on my sales work, and I just decided to start working through this. I think within a week and a half, I got to chapter 22, 23 with just enough challenge to keep me interested, but it did such a great job of teaching the material that it became very easy to do. So if you're looking for an ancillary book to help students learn the language as you're teaching your class, these are great. This paper book, I think, is $30. As you can see, it's pretty thick and it's, nice. So.
Andy, sorry.
Yes.
What? I mean, learning the Wolfram language. What is the difference between learning the Wolfram language and learning to be fluent in Mathematica?
They're the same thing. They mean the same. Those two things mean the same thing.
Okay.
The Wolfram language is what you program with in Mathematica. The capital P for plot, the manipulate, the percent sign for the last output, that is Wolfram language, but it's Mathematica syntax. Do you guys have questions about anything you've seen? Or do you have questions about other pieces of our technology stack that you've heard about that you want to talk about? All right. Well, I tell you what, I'll stop sharing. Greg, I'll let you wrap up with anything you need to say.
Sure. Thanks a lot, Andy. I appreciate it. And thanks everyone for coming in and watching. I hope if you have any questions at all, from basic to more advanced, please reach out to us. That's what we're here for. We're your support team, and appreciate it. I know Wilfredo knows a lot about these things, but if you have any questions that we can answer for him in his stead, or any ways to utilize it. One thing that we didn't have a chance to show you, we have a tremendous, what we call notebook archive. And what that means is that if you think, man, this might be a great way to use Mathematica in my classroom, chances are somebody's already thought that too, and they already have the basic kernel of a notebook created for you. Doesn't mean you can't modify it any way you want to. You certainly can, but it's a great way to start without going, okay, geez, I got to start upper left-hand corner and write the whole thing. It's a great, oh, there it is, as if by magic itself. You can just type in, for instance, I had an economics professor recently talk to me about Black-Scholes models. I was like, honestly, not an economics major, didn't know. Typed it in and boom, there's like 3 or 4 different examples already created. So just a nice place to start where you don't have to feel like you're reinventing a particular wheel. Also, we have a demonstrations project that our users have been kind enough to submit to us over the years. And once again, just a great way to get a jump start on what it is that you want to try to accomplish in class, or as a kernel to start in your research. Most of them are very basic. You're not going to find anything that necessarily moves the needle on hypothetical physics or anything like that. Stephen's already doing that if you haven't been following along in his blog. But it's again, just a real nice place where you can jump right in, tailor it to how you are most comfortable with, and then move on. So a couple of real nice ways to jumpstart what you're trying to accomplish.
Good. Any question or comment? Okay, thank you guys for spending with
Sure.
us. We will send the link of this video for people that didn't show up. And,
Correct.
And well, also you will distribute the notebook too, right?
Absolutely. Yep, we sure will. So if you have any questions, just let us know. Otherwise, we'll drop off and you can say all the bad things you want to about Andy. I won't tell him.
I thank you very much.
Have a great afternoon, everybody.
Bye.
Thank you
Bye-bye.
so much.